Basically what I'm going over today is working with schedulers, specifically the systems that we made for Vex back in December and January. And what that entails, stuff to keep in mind, how to actually write code that does multitasking and all that in an embedded system. So first of all, what is multitasking? Yeah, if you have multiple things that you want to happen at the same time, or at least appear to happen at the same time, and how you go about doing that. And the reason why I said appear to happen at the same time is often you have fewer CPUs than you have things to do, because I mean one possible way to have multiple things happening at the same time is, well, if you have 4 programs that all need to be running at the same time, just get 4 computers. Easy, right? Well, or a computer with 4 CPUs or 4 cores is really what you care about, but that's not usually feasible because often you have more than like 1 or 2 things that you want to be happening at the same time. It's not worth it. It doesn't make like financial sense to have more than to have that many cores, and a lot of the times you don't know ahead of time how many different things you're going to have running at the same time, right? So you need something at the software level to allow you to simulate multiple things happening at the same time by letting one do a bit of its processing, then another do a bit of its processing and all that. So the piece of software that actually does that, decides that when different things run, is called the scheduler. I'm not going to go over this part today, but it also mediates access to different shared resources. So if you say, okay, so we can have multiple things running at the same time, but they can't both be writing to the same file at the same time, or something like that. So there's 2 types of schedulers overall. There's preemptive schedulers, which is what you'll see in like Windows, Linux, any high-level operating system like that, where the scheduler is able to interrupt or preempt whatever is running to swap something else in. Every time I say user code, because I'm going to say that probably 100 times the next half hour, that means like the different tasks that are running on top of the scheduler. That's what it means in this context, as opposed to like the code that is part of the scheduler itself. The user code can assume, except for say if you're interacting with the scheduler to start a new task or something like that, you can basically write the code as if you have your own CPU. So you don't need to do anything special. And the other type of scheduler, cooperative. So here, so user code yields, meaning that in order for other code to run, the code that's running right now has to say, okay, I'm done what I'm doing for now, or let something else run. That includes sleeping. So if you need to say, okay, sleep for 1 second, that basically means yield, but don't give me back control immediately, give me back control at least a second from now. And also, that means it's easier to hang. So it's easier for the whole system to just stop running, because if you just put a while true with no body in this, it'll never yield, nothing else will ever run, and whatnot. So for that reason, that's why you see preemptive schedulers in like desktop operating systems, where you probably have thousands of programs running, written by probably each one written by a different development team, often from a different company, or the user can write their own code and all that. Whereas cooperative schedulers you often see in embedded systems like robots and things like that, because the advantage to having this system is that you control control yield. So you control exactly when code switches from one thing to another. So if you have a bunch of lines of code that's running on a preemptive scheduler, at any point in the middle, some other code can run, and you have to write your code keeping that in mind. So if you're looking at a global variable, say, you have another task that could be modifying that global variable, you need to keep in mind that could change, or that could get swapped out or whatnot. Whereas on a cooperative scheduler, that can't happen. If you have a bunch of lines of code and none of them tell it to yield or sleep or anything, then they're going to run in order without any other code running in between. We are going to go over cooperative scheduler in particular because that's what all of our stuff runs on. So there's a few different ways that you could structure something like this. You can have actual separate tasks or processes or whatever you want to call them that each, say, give up control, and then you can do other things and then give it back to that process when its turn comes around again. But the way we've set up our system is with a callback model. So code is structured as a bunch of callbacks. Each callback runs completely to completion before any other code runs. But that callback, as far as the scheduler is concerned, is a one-off. It is a one-off thing. It's not part of there's no long-running concept of a task that spans multiple callbacks. That's up to you to say if you want to basically have this run, and then that run, and then that run, and then that run with other things running in between. This callback needs to schedule that callback to run, which needs to schedule that callback to run, and so forth. The only interaction that the user code actually has with the scheduler is for scheduling new things. There's no sleep function. There's a schedule this function to run after this amount of time. So if you had like something resembling a flow chart, so you had a start, and then this needs to happen, and then this needs to happen, and then maybe you have some condition and it will sometimes go there, sometimes go back. If you structure it so that each of these is a separate function, and there's, say, maybe you want this to happen like immediately, but there's like a, I don't know, 10 millisecond delay there, and 5 millisecond delay there, and let's say there's some other thing going on down here. So you would structure each of these as a separate function in code, and then sometime before it returns, and of course it can call other functions just like normal C code, but sometime before it returns, this function will say, okay, scheduler, at now plus 10 milliseconds, run this function, and pass it this parameter. And then it'll return, and then the scheduler will go off doing other things, because maybe there's whole other parts of the program running, or if not, it'll just sleep the processor for 10 milliseconds, and then run this one, and then this one, sometime before it finishes, again would say, okay, 5 milliseconds from now, run this function. This function could maybe, based on some condition, it would either say, okay, run this function after 10 milliseconds, or it would say, run this function now. And this is an example of how you do a loop if you had like multiple stages. If, however, you wanted just one thing to run, say, every 10 milliseconds or something like that, if you have a long-running process, like say you're handling user input from the controller, you want to do that every 10 milliseconds. How you do that is it's equivalent to that, just on the logical extreme of making it small. You just say, at the end of that function, you say, okay, run this function in 10 milliseconds, and this function just happens to be the exact same function that you're in. And that's valid. What that would look like in like some sort of pseudocode, and we'll get into actual code later, your driver control loop, it wouldn't actually have like a while true loop in it. It would just say like get joysticks, a few more things like that, and then schedule op control in 10 milliseconds. Of course, like this is pseudocode, not actual C syntax. We're just going to do a quick aside about how you do this kind of thing in C. So a function pointer is a data type in C that represents a function that you can call. It doesn't represent any additional data or whatever, so if you've worked with something like, I don't know, Java or JavaScript, and you know, where you have like a lambda that you can capture variables from outside of it, It doesn't have any fancy features like that. It's just a function. It has possibly the worst syntax of anything in the C language. This is how, if you want to store any function that takes in an integer as its only parameter and doesn't have a return type, and want to store that in a variable called func, that's the syntax for defining that variable. It is terrible syntax. That is a variable. Its size, if you care about that, is the same size as any pointer, and it can store a reference to any function that that has that signature. So it has one parameter, and that's an int, and it has no return value. You could do func equals the address of foo. Like, you can pass these around inside structures as parameters, whatever, and then later you can just treat func as if it is an actual function, even though it's a variable, and call it passing an integer. And that, in this case, would call foo because that's the function that's referred to by func. Does that make sense? Okay, and foo is just a normal function that just has to have the same same signatures, so the same parameters and return type as that function, or as the function pointer specifies. There's a particular signature that's used very commonly in C for things like this, where you need to say, okay, when X happens, run this code, and that is very similar to what we have here, except that you have one parameter, and it is a void pointer, which really does not help the readability of this. Func is now a variable that can hold a reference to any function that has one parameter that's a void pointer and has no return value. Why? The reason is that a void pointer is kind of a catch-all. Like, we can use it to directly or indirectly pass any data. If the only data you need that the function needs in order to know what to do is a pointer, well, you can just cast that pointer to a void pointer, and then the first thing that function does is cast it back to the pointer type that it needs. If you need to pass in more complex data, well, then you just make a struct with a field for every piece of information you need to pass in, and allocate that struct, and go with it. And then what you'd actually be passing to the schedule function, or any other function that you need to say, run this code at a later point, you pass two things, in addition to whatever other scheduling information needs, like the timestamp. But for the actual function part, you need to pass two things. One is the function pointer, to tell it what function to call. Number two is a void pointer, that's what data you're passing in. If that, say, needed, like, I don't know, 2 ints and a float in order to do whatever processing it does, then your code would look something like this. So you'd have a struct, you'd allocate, and then you can fill in data x equals whatever, and data y equals, and data z equals. And then later, you would schedule, and you'd pass in foo, like the address of foo as a function to call, and this data parameter as the actual piece of data to call. And then the one thing here is that foo at the very end needs to remember to free that data, otherwise you have a memory leak. The common mistake to make is, instead of calling malloc, to just create a local variable of this structure type, and then use just use the address of that local variable. The reason that does not work is the local variable only exists at that address in memory so long as the function is running, and the key feature of our scheduler is that anything we schedule won't actually get called until after the current function exits. We know that, right? Because we said it's a cooperative scheduler. It does not, it's not going to stop what I'm doing right now to run some other code. It's going to wait until the current callback is done, and then it'll call it. So we know that we're going to need access to this data after the current function exits. So you can't just use a local variable, because that won't exist anymore by that time. C will let you, which is why very high-level things are not written in C, because it's really easy to make mistakes like that. But that won't work. By C will let you, I just mean, like, you won't get a compiler error. It's valid C code, but it won't work. If foo always frees data, data, then you can't use data somewhere else that may run after foo, because foo will have freed it and then could be used for some other